There's a substance on Earth that completely breaks the rules of physics, and global reserves have dropped 34% since 2020 from 48.2 billion to just 31.7 billion cubic meters. While most people think of helium as balloon filler, the 2025 global helium crisis threatens to shut down MRI machines worldwide. Helium forms only through radioactive decay over millions of years. Unlike other gases, there's no way to make more. But that's not even the strangest part. Cool helium down to just 2.17 Kelvin, and it transforms into a state physics didn't think possible at human scales, a liquid that climbs walls, flows upward against gravity, and has zero friction. Scientists call it superfluid helium, and the numbers behind this crisis are staggering. The 2025 Helium Crisis, numbers that will shock you. Global helium reserves have plummeted to their lowest levels in recorded history by 2025, with proven reserves dropping from 48.2 billion cubic meters in 2020 to just 31.7 billion cubic meters today. This represents a catastrophic 34% decline in just 5 years, a rate of depletion that has stunned industry experts and government officials worldwide. The United States Geological Survey's latest assessment reveals that at current consumption rates, these remaining reserves will last only 15 to 20 years, fundamentally altering humanity's relationship with this irreplaceable element. Current global helium consumption has reached 8.2 billion cubic meters annually, while production has stagnated at just 6.8 billion cubic meters per year. This massive supply-demand imbalance means the world consumes 1.4 billion cubic meters more helium than it produces every single year, forcing industries to drain strategic reserves that took millions of years to accumulate naturally. The gap continues widening as semiconductor manufacturing, medical imaging, and emerging quantum computing applications drive demand higher each quarter. Traditional helium extraction sites face unprecedented challenges that have reshaped the global supply map. Qatar's North Field, which provided nearly 30% of world helium production through 2023, reduced output by 45% due to new liquefied natural gas priorities and infrastructure maintenance issues. Russia's Amur facility, designed to supply 20% of global demand, operates at only 60% capacity following international sanctions and technical difficulties with cryogenic separation equipment. Algeria's Hassi R'Mel complex, another major source, suspended helium extraction for 8 months in 2024 due to political instability and equipment failures. The United States remains the world's largest helium producer, extracting approximately 2.9 billion cubic meters annually from natural gas operations across Texas, Kansas, and Oklahoma. However, American production peaked in 2019 and has declined steadily as natural gas wells age and helium concentrations decrease. The Bureau of Land Management's Cliffside facility, which stored helium for decades, completed its mandated sell-off in 2021, eliminating the strategic buffer that once stabilized global markets during supply disruptions. Poland emerged as an unexpected player in 2024, beginning commercial helium extraction from newly discovered deposits near Podlaskie. Initial production rates of 12 million cubic meters annually provide only minimal relief to European shortages. Tanzania's Rukwa project shows promise with estimated reserves of 54 billion cubic feet, but extraction infrastructure remains years away from commercial operation. These new sources cannot compensate for declining production from established fields. Helium's unique atomic structure makes artificial production impossible through any known chemical or physical process. Unlike hydrogen, which can be manufactured through electrolysis, or nitrogen, which can be separated from air, helium forms only through radioactive decay of uranium and thorium deep within Earth's crust over geological timescales. This natural production process creates approximately 3,000 tons of helium globally each year, a microscopic fraction of human consumption. Once helium escapes into the atmosphere, it rises beyond Earth's gravitational pull and disappears into space forever, making conservation absolutely critical. The economic impact of helium scarcity has transformed entire industries within just 5 years. Laboratory-grade helium prices increased from $4.50 per cubic meter in 2020 to $34.80 per cubic meter in 2025, representing a staggering 673% price increase. Ultra-high purity helium required for semiconductor manufacturing now costs $89.20 per cubic meter compared to $12.30 in 2020. These price increases force difficult decisions about which applications receive priority access to remaining supplies. Medical facilities worldwide face impossible choices as helium costs consume larger portions of operating budgets. St. Mary's Hospital in London spent $127,000 on helium in 2020, but allocated $486,000 for the same quantity in 2025. Similar increases affect hospitals across Europe, Asia, and North America, with some facilities reducing MRI availability by 40% to control costs. Research institutions postpone low-temperature physics experiments, while universities eliminate liquid helium demonstrations from introductory courses. Manufacturing sectors dependent on helium experience severe disruptions as procurement becomes increasingly difficult. Fiber optic cable production requires helium atmospheres to prevent contamination, but suppliers now ration deliveries and require 6-month advance contracts. Welding operations for aerospace and nuclear applications struggle to secure helium-argon mixtures essential for titanium and aluminum joining processes. Semiconductor fabs implement elaborate helium recycling systems, recovering and purifying used gas that would have been vented to atmosphere in previous decades. The helium crisis intensifies urgency around understanding this element's most extraordinary properties, particularly those exhibited under extreme cooling conditions. Scientists recognize that developing more efficient helium recycling technologies requires deeper comprehension of how helium behaves at various temperatures and pressures. Current recycling methods recover only 85% of helium from closed-loop systems, meaning 15% still escapes during each cycle. Improving recovery rates to 98% or higher could extend available supplies by decades, while new sources come online. Research into helium's quantum mechanical properties offers potential pathways to revolutionary cooling technologies that might reduce overall helium consumption. Advanced magnetic refrigeration systems, thermoacoustic coolers, and pulse tube refrigerators show promise for applications currently requiring continuous helium flow. However, these alternatives cannot match the cooling power and temperature stability that liquid helium provides for superconducting magnets and quantum computing systems. The most fascinating aspect of helium's behavior emerges only when this already exotic element undergoes transformation at temperatures approaching absolute zero. While helium gas seems relatively ordinary despite its chemical inertness, cooling it to liquid form reveals properties that challenge fundamental understanding of matter itself. These properties become more pronounced as temperatures drop further, suggesting that helium's strangest secrets remain locked behind barriers of extreme cold. Understanding exactly what happens to helium under these extreme conditions has become more than academic curiosity. As global supplies dwindle and prices soar, every aspect of helium's behavior gains practical importance for developing conservation strategies and alternative technologies. The quantum mechanical effects that govern superfluid formation might hold keys to creating more efficient cooling systems or entirely new approaches to low-temperature physics applications. Yet, before helium can reveal its most impossible properties, it must first overcome its fundamental reluctance to cooperate with anything at all. This element's stubborn independence makes it one of the most difficult substances on Earth to work with, requiring extreme measures just to force it into liquid form. Why helium refuses to play by the rules. This antisocial behavior stems from helium's atomic architecture, where 2 electrons occupy a completely filled outer shell around a nucleus containing 2 protons and 2 neutrons. Unlike other elements that eagerly share, donate, or accept electrons to achieve stability, helium already possesses the perfect electron configuration that all other atoms strive to reach. This complete shell creates an atom so content with its current state that it ignores every chemical advance from neighboring elements. The noble gas family includes neon, argon, krypton, xenon, and radon, but helium represents the most extreme example of chemical aloofness within this exclusive group. While other noble gases can form compounds under extraordinary conditions involving fluorine or extreme pressures, helium maintains its independence regardless of circumstances. Scientists have attempted to force helium into chemical relationships using powerful electric fields, crushing pressures, and reactive partners, yet helium consistently emerges from these experiments unchanged and unbound. This chemical indifference creates profound consequences when attempting to change helium from gas to liquid. Most gases liquefy when their atoms draw close enough together that intermolecular forces overcome thermal motion. Oxygen molecules possess slight electrical imbalances that create attractive forces between neighboring molecules. Water vapor condenses readily because hydrogen bonding provides strong intermolecular attraction. Helium atoms, however, present perfectly spherical electron clouds with no permanent electrical charges, creating no mechanism for mutual attraction. The only force capable of pulling helium atoms together operates through van der Waals interactions. These forces arise when electrons spontaneously cluster on one side of an atom for brief moments, creating temporary electrical imbalances that generate weak attractive forces with nearby atoms. Van der Waals forces represent fleeting interactions, providing the minimal attraction necessary to bring helium atoms into close proximity. The weakness of van der Waals forces becomes apparent when comparing helium's liquefaction temperature with other gases. Nitrogen transforms from gas to liquid at 77 Kelvin, while oxygen liquefies at 54 Kelvin and hydrogen at 33 Kelvin. These temperatures, though extremely cold by human standards, seem tropical compared to helium's liquefaction point of 4.2 Kelvin, just 4.2 degrees above absolute zero. Reaching 4.2 Kelvin requires specialized equipment and careful technique as heat flows into the system from every possible source. Room temperature radiation, vibrations through support structures, and electrical connections contribute unwanted thermal energy that threatens to vaporize liquid helium instantly. Cooling systems must remove this heat continuously while maintaining temperatures within a narrow range where van der Waals forces barely exceed thermal motion energy. Converting liquid helium into solid form presents even greater challenges, requiring pressures exceeding 25 times normal atmospheric pressure. These extreme conditions reflect the minimal attractive forces between helium atoms, which require external compression to force them into rigid crystalline arrangements. Even under crushing pressures, solid helium maintains unusual properties, including the ability to flow through its own crystal lattice under certain conditions. The specific isotope of helium determines its quantum mechanical behavior at extremely low temperatures. Helium-4, containing 2 protons, 2 neutrons, and 2 electrons, represents the most common isotope found in natural gas deposits. This particular combination creates what physicists classify as a boson, a particle type that follows quantum mechanical rules allowing multiple atoms to occupy identical energy states simultaneously. When cooled sufficiently, helium-4 atoms can merge their quantum identities, creating collective behaviors impossible for individual particles. Helium-3, containing 2 protons, 1 neutron, and 2 electrons, exhibits fundamentally different quantum properties despite its chemical similarity to helium-4. This isotope functions as a fermion, following quantum rules that prevent multiple atoms from sharing identical states. The Pauli exclusion principle governs fermion behavior, requiring each particle to maintain a unique quantum identity even at extremely low temperatures. These quantum mechanical differences between helium-3 and helium-4 lead to dramatically different behaviors when cooled to near absolute zero. Liquid helium at 4.2 Kelvin exhibits several peculiar characteristics that distinguish it from ordinary liquids. Its density measures only 0.126 grams per cubic centimeter, roughly 1/8 the density of water, making it lighter than most organic solvents. This low density creates unusual visual effects, as objects that normally sink in water float easily on liquid helium surface. The refractive index of liquid helium measures 1.025 compared to air, creating minimal light bending that makes the liquid surface nearly invisible to human observers. Detecting the presence of liquid helium often requires indirect methods, as its transparent nature and low surface tension prevent the formation of visible surface reflections typical of other liquids. Laboratory workers frequently use small floating objects or temperature sensors to confirm the presence of liquid helium in containers, as visual confirmation proves unreliable even under controlled lighting conditions. These unusual properties represent only the beginning of helium's strange behavior at cryogenic temperatures. The quantum mechanical effects that govern helium-4's boson nature remain largely dormant at 4.2 Kelvin, suppressed by thermal motion that prevents atoms from achieving the coherent states necessary for collective quantum behavior. As temperatures drop below this initial liquefaction point, thermal energy decreases until quantum effects begin influencing macroscopic properties. The transformation becomes dramatic when cooling continues toward a critical temperature where liquid helium undergoes a phase transition unlike any other known substance. This boundary marks where ordinary liquid behavior gives way to quantum mechanical phenomena operating at human visible scales, creating a substance that simultaneously exhibits characteristics of both normal liquids and quantum mechanical systems. At this critical point, liquid helium begins displaying effects that appear to violate fundamental physical laws, transforming from merely unusual to genuinely impossible by conventional physics standards. The Lambda point, where physics gets weird, this critical temperature boundary occurs at precisely 2.17 Kelvin, a point scientists call the Lambda point due to the distinctive Greek letter shape that appears when plotting helium's heat capacity against temperature. The name captures the sharp peak that forms at this exact transition point, marking where liquid helium transforms into something that operates by completely different rules. This temperature sits just 1.97 degrees above absolute zero, requiring extraordinary cooling systems to achieve and maintain. Witnessing the Lambda point transition creates an eerie spectacle that has captivated physicists for decades. Liquid helium at 4.2 Kelvin bubbles vigorously as heat input causes localized boiling, creating the familiar sight of vapor bubbles rising through the liquid just like water boiling in a kettle. Scientists carefully monitor temperature readings as they continue cooling the liquid helium toward the Lambda point, watching for the moment when everything changes. As the temperature approaches 2.17 Kelvin, the violent bubbling begins to subside, and then, in an instant that seems to defy explanation, all bubbling stops completely. This sudden stillness signals the birth of helium-2, a substance that no longer follows the physical laws governing ordinary matter. The transition happens so abruptly that observers often question whether their cooling equipment has malfunctioned, as the liquid surface becomes mirror-smooth and completely motionless. No vapor bubbles form, no surface disturbances occur, and the liquid appears frozen in time despite remaining fluid. Scientists describe this moment as witnessing the emergence of a quantum mechanical state at macroscopic scales, where the collective behavior of billions of atoms becomes governed by quantum effects normally invisible to human observation. The most remarkable change occurs in helium's thermal conductivity, which increases by approximately 1 million times at the Lambda point. This extraordinary enhancement transforms helium from a relatively poor heat conductor into the most efficient heat transfer medium known to science. To understand the magnitude of this change, consider that copper, one of the best metallic heat conductors, transfers heat roughly 400 times less efficiently than helium-2. Even diamond, which holds the record for thermal conductivity among solid materials, cannot match the heat transfer capabilities of this quantum liquid. This incredible thermal conductivity explains why helium-2 refuses to boil under normal heating conditions. When energy enters ordinary liquids, it creates localized hot spots that form vapor bubbles, causing the familiar bubbling associated with boiling. The poor thermal conductivity of regular liquids means heat cannot spread quickly enough to prevent these temperature variations from developing. Helium-2 operates under entirely different principles, instantly distributing any heat input throughout its entire volume with such efficiency that temperature differences cannot establish themselves anywhere within the liquid. The mechanism behind this impossible heat transfer involves a phenomenon called second sound, where thermal energy travels through helium-2 in wave-like pulses rather than through conventional convection or conduction. Normal heat transfer relies on faster-moving molecules colliding with slower ones, gradually spreading thermal energy through random molecular interactions. Second sound represents a fundamentally different process where heat propagates as organized waves traveling at specific velocities through the quantum liquid. Soviet physicist Pyotr Kapitsa conducted the groundbreaking experiments in the late 1930s that revealed the true nature of heat transport in helium-2. His experimental setup involved placing two electrical resistors separated by a small distance within a container of superfluid helium. By generating controlled thermal pulses with one resistor and detecting the arrival of heat waves with the second resistor, Kapitsa demonstrated that thermal energy travels through helium-2 at precisely the speed of sound within the liquid. These measurements revealed that second sound propagates at approximately 20 meters per second through helium-2 at the lambda point, a velocity that corresponds exactly to the speed of sound in the superfluid. This discovery provided the first direct evidence that heat transport in quantum liquids operates through wave mechanics rather than particle diffusion. The implications of this finding suggested that thermal energy behaves like sound waves in helium-2, traveling in organized pulses that maintain their coherence across macroscopic distances. The wave-like nature of second sound creates practical consequences that distinguish helium-2 from every other known liquid. When heat enters one region of a container filled with superfluid helium, thermal waves immediately propagate outward in all directions, reaching every corner of the container simultaneously. This instantaneous heat distribution prevents the formation of temperature gradients that would normally drive convection currents or create boiling instabilities in regular liquids. Scientists can observe second sound directly using sensitive temperature sensors placed at different locations within containers of helium-2. Applying a brief heat pulse to one sensor creates thermal waves that arrive at distant sensors with perfect timing precision, confirming that heat travels at constant velocity through the quantum medium. These experiments demonstrate that thermal transport in superfluids follows wave equations similar to those governing sound propagation in gases or vibrations in solid materials. This extraordinary thermal behavior emerges from the quantum mechanical nature of helium-2, where individual atoms lose their separate identities and merge into a collective quantum state. The wave function describing this collective state extends throughout the entire liquid volume, enabling thermal disturbances to propagate through quantum mechanical processes rather than classical molecular interactions. This quantum coherence allows thermal energy to move through the liquid without relying on random atomic collisions or molecular diffusion. The transition to helium-2 at the lambda point represents only the beginning of increasingly strange behaviors that emerge as quantum effects dominate macroscopic properties. While the incredible thermal conductivity and second sound phenomena already challenge conventional understanding of liquid behavior, the same quantum coherence that enables instantaneous heat transport also governs how helium-2 responds to mechanical forces. This creates a substance whose flow properties appear to contradict everything scientists understand about how liquids should behave when forced through confined spaces. Zero viscosity, the liquid that flows like a ghost. The most startling demonstration of helium-2's impossible properties occurs when scientists attempt to contain it using materials with microscopic pores. Standard laboratory filters made from sintered ceramic contain countless tiny openings measuring just a few micrometers across, far smaller than the width of human hair. These pores easily stop ordinary liquids, creating effective barriers that prevent flow through the ceramic material. Water, alcohol, liquid nitrogen, and every other known liquid encounters insurmountable resistance when forced against these microscopic barriers. Helium-2, however, passes through these same ceramic filters as if they were completely absent, flowing with absolutely no impediment or reduction in speed. Viscosity governs how every liquid moves through our daily experience, determining whether substances pour like water or flow like honey. This fundamental property measures internal friction between molecules as they slide past each other during movement. Thick motor oil exhibits high viscosity because its long molecular chains tangle and resist separation, requiring significant force to maintain flow. Water possesses much lower viscosity, allowing molecules to move past each other with minimal resistance. Even gases display measurable viscosity, though much lower than liquids due to greater molecular spacing that reduces intermolecular interactions. The mathematical measurement of viscosity uses units called poise, named after French physicist Jean Poiseuille, who studied fluid dynamics in the 19th century. Water at room temperature measures approximately 0.01 poise, while honey registers around 100 poise, demonstrating the enormous range this property spans across different substances. Liquid helium at 4.2 Kelvin exhibits measurable viscosity of roughly 0.0000025 poise, making it less viscous than hydrogen gas. These measurements follow predictable patterns based on molecular structure and temperature, allowing scientists to calculate expected flow rates through pipes, valves, and other restrictions. Helium-2 shatters these established patterns by registering exactly zero viscosity on every measurement instrument devised by physicists. Precision viscometers capable of detecting resistance forces smaller than the weight of individual atoms show no measurable friction when helium-2 flows through their calibrated chambers. This complete absence of internal resistance creates a true superfluid that moves without any energy loss due to molecular friction. The implications of zero viscosity extend far beyond academic measurements, enabling behaviors that appear to violate basic principles of fluid mechanics. The classic sintered ceramic experiment reveals the profound difference between normal liquid behavior and superfluid properties. Researchers prepare identical containers filled with various liquids cooled to extremely low temperatures, then insert ceramic discs containing billions of microscopic pores into the bottom of each container. Liquid nitrogen, liquid hydrogen, and regular liquid helium remain trapped above their respective ceramic barriers, unable to penetrate the tiny openings despite gravity pulling downward. Scientists can wait hours or days without observing any significant drainage through the ceramic material. The same ceramic disc placed in helium-2 produces dramatically different results. The superfluid immediately begins flowing through every microscopic pore simultaneously, draining the container as rapidly as if no barrier existed whatsoever. Flow rates through the ceramic match those observed when liquid pours through completely open passages of equivalent cross-sectional area. This behavior suggests that helium-2 experiences no resistance from the pore walls, flowing as freely through micrometer-wide channels as through centimeter-wide openings. Advanced experiments using ceramic materials with progressively smaller pore sizes reveal that helium-2 maintains its frictionless flow regardless of opening dimensions. Pores measuring just 50 nanometers across, roughly 2,000 times smaller than the width of human hair, present no obstacle to superfluid flow. Even barriers with openings approaching molecular dimensions fail to impede helium-2 movement, demonstrating that this quantum liquid behaves more like a ghost than ordinary matter when encountering physical obstacles. The quantum mechanical foundation for this frictionless flow emerges from a phenomenon called Bose-Einstein condensation, where helium-4 atoms merge their individual quantum identities into a single collective state. Below the Lambda point, billions of helium atoms occupy identical quantum energy levels, creating a macroscopic wave function that extends throughout the entire liquid volume. This quantum coherence eliminates the random molecular motions responsible for viscosity in normal liquids, allowing all atoms to move in perfect synchronization without internal friction. Wolfgang Ketterle, Nobel Prize winner for achievements in atomic physics, provides a helpful analogy for understanding this quantum harmony. He compares normal liquid flow to people walking randomly through a crowded marketplace, constantly bumping into each other and experiencing friction that impedes overall movement. Superfluid flow resembles a perfectly synchronized marching band where every member moves in lockstep, eliminating collisions and resistance that would slow the group's progress. This collective motion allows the entire liquid to respond instantaneously to external forces without internal energy losses. Temperature plays a crucial role in maintaining the quantum coherence required for zero viscosity. As temperatures rise above the Lambda point, thermal energy disrupts the collective quantum state, causing individual atoms to break away from the synchronized motion. This transition gradually restores normal viscosity as increasing numbers of atoms revert to independent behavior. The superfluid component decreases proportionally with rising temperature until normal liquid properties dominate completely above 2.17 Kelvin. The zero viscosity property creates a foundation for even more extraordinary behaviors that challenge fundamental assumptions about liquid dynamics. Frictionless flow enables helium-2 to move through spaces and configurations impossible for normal liquids, including pathways that appear to violate energy conservation and gravitational effects. Scientists observe flow patterns that seem to ignore external forces, with liquid moving upward, sideways, and through complex geometric arrangements without apparent energy sources driving the motion. These impossible flow characteristics prepare observers for visual demonstrations that challenge everything they understand about how liquids interact with their containers, creating gravity-defying stunts where the very concept of containment becomes meaningless. Laboratory demonstrations reveal these quantum mechanical principles through direct, visual observation of liquid behavior that contradicts every expectation. The most visually stunning demonstration occurs when scientists attempt to contain helium-2 in open vessels. Unlike every other liquid known to science, helium-2 refuses to remain confined within container walls, instead creeping steadily upward against gravitational forces that should pull it downward. This upward migration creates a mesmerizing spectacle where liquid appears to flow backward through time, ascending vertical surfaces with relentless determination until it reaches container edges and spills over onto laboratory benches below. The mechanism driving this gravity-defying behavior involves the formation of an extraordinarily thin film measuring just a few atoms in thickness across all surfaces contacting the superfluid. This microscopic layer spreads uniformly over glass, metal, ceramic, and plastic materials, creating an invisible pathway for liquid transport that operates independently of bulk fluid behavior. The film thickness remains constant regardless of container geometry or surface orientation, maintaining its atomic scale dimensions whether coating horizontal bottoms or vertical walls. Van der Waals forces provide the adhesive mechanism that binds this ultra-thin film to container surfaces, creating weak but sufficient attraction between helium atoms and surface molecules. These same forces that barely hold liquid helium together in bulk form become dominant at the film surface interface, where reduced dimensionality amplifies their relative importance. The quantum nature of helium-2 eliminates viscosity within this film, allowing frictionless flow through pathways that would completely block normal liquid movement. Surface tension effects in ordinary liquids create meniscus formations that curve upward or downward depending on adhesive and cohesive force balance. Water forms concave menisci against clean glass because molecular attraction to glass exceeds water's internal cohesion. Mercury creates convex menisci because its strong internal bonding overwhelms surface adhesion forces. Helium-2 operates under completely different principles, forming films that ignore traditional surface tension limitations and spread uniformly across all available surfaces regardless of material properties. The visual experience of watching helium-2 climb container walls challenges fundamental assumptions about liquid behavior. Scientists describe observing liquid levels that drop continuously in central container regions while simultaneously rising along perimeter walls, creating impossible flow patterns that appear to violate mass conservation. The ascending film moves steadily upward at rates measuring several millimeters per minute, fast enough for human observation, yet slow enough to track individual progress increments. Open containers filled with helium-2 cannot maintain their contents for extended periods as the climbing film inevitably reaches container edges and begins dripping onto surrounding surfaces. Laboratory workers must use specialized closed systems with carefully designed geometries to prevent superfluid escape through film migration. Even microscopic scratches or surface irregularities provide pathways for film flow, making perfect containment extremely challenging to achieve in practice. The self-siphoning phenomenon represents perhaps the most dramatic demonstration of film flow properties. Researchers insert U-shaped glass tubes, partially filled with fine powder such as jeweler's rouge, into containers of helium-2, creating configurations that should remain stable indefinitely according to classical fluid mechanics. The powder particles provide numerous surface pathways for film formation while preventing bulk liquid flow through tube openings. Within minutes of insertion, the tubes begin automatically draining helium from their containers despite no external pumping or siphoning action. This self-draining effect occurs because helium-2 films form continuously along all glass surfaces within the powder-filled tubes, creating connected pathways from container interiors to external environments. The superfluid flows through microscopic spaces between powder particles, using film transport mechanisms to bypass bulk liquid restrictions that would stop normal fluids completely. Scientists can observe liquid levels dropping steadily in source containers while helium drips from tube exits, creating perpetual drainage systems that operate without external energy input. Temperature variations affect film formation and transport properties, with optimal climbing rates occurring near the Lambda point where superfluid fractions reach maximum values. As temperatures rise above 2.17 Kelvin, thermal energy disrupts quantum coherence required for frictionless film flow gradually, reducing climbing velocities until normal liquid behavior dominates. Conversely, cooling below the Lambda point enhances superfluid properties and accelerates film transport rates up to practical limits imposed by heat transfer from surrounding environments. Experimental demonstrations using transparent containers allow direct observation of the film climbing process under controlled lighting conditions. High-intensity illumination reveals the advancing film edge as it progresses up container walls, appearing as a faint line that moves steadily upward against gravitational forces. The film surface remains perfectly smooth and uniform, showing no irregularities or variations that would indicate turbulence or instability during the climbing process. The contradiction between this gravity-defying behavior and fundamental physical principles creates ongoing debates among physicists studying superfluid properties. Classical thermodynamics predicts that liquids should flow from high gravitational potential energy to low potential energy, moving downward rather than upward when no external work is performed. Helium-2 violates these predictions by spontaneously climbing to higher gravitational potential states, apparently creating energy from nothing while maintaining perfect stability. Understanding film flow properties has become crucial for developing practical applications of superfluid technology. Helium conservation systems must account for film-based losses that occur even in supposedly sealed containers. These engineering challenges require detailed knowledge of how quantum liquids interact with various surface materials under different temperature and pressure conditions. Yet, the wall climbing phenomenon represents only one aspect of helium-2's contradictory nature. Scientists have discovered that this same liquid exhibiting perfect frictionless flow can simultaneously display completely different behaviors when subjected to mechanical forces, revealing internal complexities that challenge the very concept of a single, unified quantum state. The spinning paradox, when helium-2 contradicts itself. The paddle wheel experiment demonstrates this complexity through direct mechanical interaction. Scientists place a metal cylinder inside a container of helium-2 and spin it using an external electromagnetic field. A lightweight paddle wheel sits nearby, completely separate from the rotating cylinder with no mechanical connections between the two objects. According to basic fluid dynamics, nothing should happen to the paddle wheel since helium-2 exhibits zero viscosity and cannot transfer momentum between objects. Yet, within moments of starting the cylinder's rotation, the paddle wheel begins turning in the same direction, spinning faster as the cylinder's rotation speed increases. This momentum transfer should be impossible given everything demonstrated about helium-2's frictionless properties. Zero viscosity means no internal friction exists to couple the motion of one object to another through fluid intermediaries. Water can turn paddle wheels because viscous forces create drag that moves fluid layers, which then push against paddle surfaces. Oil works even better due to higher viscosity that provides stronger coupling between rotating machinery and surrounding liquid. Helium-2 supposedly lacks any mechanism for transmitting rotational motion from one object to another through fluid interactions. The experimental setup reveals the fundamental contradiction at the heart of superfluid behavior. Scientists use identical containers, electromagnetic spinning systems, and paddle wheels to test various liquids at extremely low temperatures. Liquid nitrogen, liquid hydrogen, and regular liquid helium all behave predictably, with paddle wheels remaining stationary unless viscous coupling provides sufficient momentum transfer. Higher viscosity liquids produce faster paddle wheel rotation, while lower viscosity fluids generate weaker coupling effects. These results follow established patterns based on molecular friction and fluid dynamics principles. Helium-2 completely violates these established patterns by simultaneously exhibiting zero viscosity in flow experiments while demonstrating finite viscosity in rotational systems. The same liquid that passes through microscopic pores without resistance somehow transfers momentum between separated objects, suggesting viscous interactions that should not exist. This contradiction baffled physicists for decades, as no existing theory could explain how identical substances could display completely opposite properties under different experimental conditions. The boundary layer effect provides the key to understanding this paradoxical behavior. When the metal cylinder rotates within helium-2, a thin layer of liquid adheres to the cylinder's surface through van der Waals forces and surface interactions. This boundary layer moves with the cylinder, creating localized flow patterns that extend outward into the surrounding fluid. Unlike bulk superfluid flow that exhibits zero viscosity, boundary layer interactions involve finite viscous forces that can transfer momentum to nearby objects. Scientists spent decades attempting to reconcile these contradictory observations before developing the revolutionary two-fluid model that finally explained helium-2's impossible behavior. This theoretical framework proposed that superfluid helium does not consist of a single homogeneous liquid, but rather represents two completely different fluids occupying the same physical space simultaneously. These interpenetrating components possess entirely different properties, with one behaving like a normal viscous liquid while the other maintains perfect superfluid characteristics. The normal fluid component carries all thermal energy and entropy within the system, responding to temperature changes and external forces according to classical fluid dynamics principles. This component exhibits finite viscosity, can transfer momentum between objects, and behaves much like any ordinary liquid at extremely low temperatures. The normal fluid density increases with rising temperature, becoming the dominant component as conditions approach the lambda point from above. The superfluid component operates according to completely different rules, possessing zero entropy and zero viscosity while maintaining perfect frictionless flow properties. This component cannot carry thermal energy or respond to temperature gradients in conventional ways. The superfluid density decreases with rising temperature, reaching maximum values at the lowest achievable temperatures below the lambda point. These two components coexist within identical volumes, creating a quantum liquid with dual personalities. The proportion of normal fluid versus superfluid components varies dramatically with temperature and external conditions. At the lambda point, approximately 6% of the liquid consists of normal fluid, while 94% exhibits superfluid properties. As temperatures drop further below 2.17 Kelvin, the normal fluid fraction decreases, while the superfluid component grows, reaching nearly 100% superfluid behavior at temperatures approaching absolute zero. This temperature dependence explains why different experiments reveal different viscosity properties depending on their specific conditions. Rotational experiments primarily interact with the normal fluid component through boundary layer effects and momentum transfer mechanisms. The spinning cylinder creates circulation patterns that couple to the viscous normal fluid, allowing momentum transmission to nearby paddle wheels through classical hydrodynamic processes. Meanwhile, the superfluid component remains largely unaffected by rotational motions, maintaining its frictionless properties throughout the experiment. Flow experiments through microscopic pores primarily utilize the superfluid component, which passes through barriers without resistance while the normal fluid remains trapped by viscous forces. The zero viscosity measurements reflect superfluid properties, while momentum transfer effects demonstrate normal fluid behavior. Both components exist simultaneously, but different experimental configurations preferentially interact with one component over the other. The quantum mechanical basis for this dual nature emerges from Bose-Einstein condensation effects that create macroscopic occupation of single quantum states. Helium. For atoms that participate in the condensate form the superfluid component, moving in perfect quantum coherence without internal friction. Atoms outside the condensate retain individual quantum identities, creating the normal fluid component with finite viscosity properties. The relative populations of condensed versus non-condensed atoms determine the ratio between superfluid and normal fluid components. Understanding this dual nature provides the foundation for comprehending demonstrations that appear to challenge the most fundamental laws of physics. When these two components work together under specific conditions, They create behaviors that seem to violate basic principles governing energy flow and thermodynamic equilibrium, producing visual spectacles that have amazed scientists for generations. The fountain effect, breaking thermodynamics. The most spectacular demonstration occurs when scientists shine light onto a specially designed glass apparatus submerged in the superfluid. The experimental setup consists of a hollow glass stem connected to a bulb at its lower end, with the bulb packed tightly with jeweler's rouge, a fine abrasive powder used in polishing precious metals. This powder creates countless microscopic pathways through which superfluid can flow while preventing bulk liquid movement. When researchers direct even modest heat sources like flashlight beams onto the bulb, liquid helium begins spraying dramatically upward through the stem, creating a fountain that defies every expectation based on conventional physics. The fountain reaches heights of several centimeters, with liquid streaming continuously from the tube opening as long as heat application continues. Scientists can control fountain intensity by adjusting heat input, creating taller streams with brighter lights or stronger heat sources. The effect works with various heat sources, including incandescent bulbs, focused sunlight, and even body heat from researchers' hands held near the apparatus. The response time between heat application and fountain initiation measures just seconds, demonstrating the immediate connection between thermal input and liquid ejection. This fountain effect represents a direct violation of the second law of thermodynamics, one of physics' most fundamental principles. The heated bulb creates the warmest region within the experimental system, while the surrounding liquid helium bath maintains much lower temperatures. According to thermodynamic principles established over centuries of scientific observation, liquids should flow spontaneously from hot regions toward cold areas, seeking thermal equilibrium through natural processes. Heat engines, refrigerators, and every thermal device ever constructed operate based on this principle that thermal energy moves from high-temperature sources to low-temperature sinks. The second law of thermodynamics governs energy flow direction in every natural process observed throughout the universe. Stars radiate energy outward from their blazing cores toward cold space. Hot coffee cools by transferring thermal energy to surrounding air. Ice cubes melt by absorbing heat from warmer beverages. These processes occur spontaneously because they increase total entropy, the measure of disorder within any system. The second law states that entropy always increases in isolated systems, providing the fundamental arrow of time that distinguishes past from future events. Entropy quantifies the unavailable energy within any system, representing thermal energy that cannot perform useful work. When hot and cold objects reach thermal equilibrium, their combined entropy exceeds the sum of their individual entropies before contact. This entropy increase occurs because thermal energy spreads more evenly throughout the system, reducing the temperature differences that enable work extraction. Steam engines harness entropy changes to convert heat into mechanical motion, but always generate more entropy than they consume, making perpetual motion machines impossible. The fountain effect appears to create a perpetual motion device that extracts work from thermal reservoirs without increasing total entropy. The heated bulb provides thermal energy that somehow pumps liquid helium upward against gravitational forces, performing mechanical work without apparent energy costs. If this process operated through conventional thermodynamic mechanisms, it would require energy input exceeding the gravitational potential energy gained by lifting liquid to fountain heights. Yet, the fountain operates using minimal heat input, suggesting efficiency levels that challenge energy conservation principles. Scientists initially questioned whether the second law of thermodynamics contained fundamental errors when confronted with fountain effect observations. The law had withstood countless experimental tests since its formulation in the 19th century, forming the foundation for understanding heat engines, chemical reactions, and stellar evolution. No previous observations had revealed processes that decreased entropy spontaneously, making the fountain effect a profound challenge to established physics. Researchers conducted extensive measurements to verify whether energy conservation and entropy principles actually failed in superfluid systems. The resolution to this apparent paradox emerges from the unique entropy properties of the superfluid component within helium-2. The The two-fluid model reveals that only the normal fluid component carries entropy, while the superfluid component maintains exactly zero entropy regardless of temperature or pressure conditions. This entropy-free nature allows the superfluid to flow against temperature gradients without violating thermodynamic principles, since no entropy transport accompanies the liquid motion. When heat enters the bulb region, it increases the local temperature and expands the normal fluid component at the expense of the superfluid fraction. The normal fluid component responds to temperature increases by moving toward thermal equilibrium, flowing away from the heat source toward cooler regions. Simultaneously, the superfluid component flows in the opposite direction toward the heat source, maintaining mass conservation while creating counterflow patterns that drive the fountain mechanism. The jeweler's rouge powder plays a crucial role by creating a selective barrier that permits superfluid flow, while blocking normal fluid movement. The microscopic pores between powder particles provide pathways small enough that only the zero viscosity superfluid component can penetrate, while the viscous normal fluid remains trapped within the bulb region. This selective permeability concentrates the superfluid flow through the narrow stem, creating sufficient pressure to drive liquids several centimeters upward against gravitational forces. The entropy balance remains consistent with thermodynamic principles because the superfluid component transports no entropy during its upward flow. Heat input increases entropy within the bulb region by expanding the normal fluid component, but this entropy remains localized and does not accompany the fountain flow. The overall system entropy increases as required by the second law, while the fountain operates through entropy-free transport mechanisms unavailable to ordinary liquids. The quantum mechanical foundation for this entropy-free flow emerges from the collective quantum state shared by all superfluid atoms. Unlike normal liquids where each molecule possesses individual thermal motion contributing to entropy, superfluid atoms occupy identical quantum energy levels that eliminate random thermal fluctuations. This quantum coherence prevents entropy generation during superfluid motion, enabling flow patterns impossible for classical fluids. The fountain effect demonstrates how quantum mechanical principles create macroscopic behaviors that appear to violate classical physics while remaining consistent with fundamental conservation laws. This spectacular phenomenon provides direct evidence that quantum effects extend far beyond atomic scales, governing the behavior of liquid volumes measuring milliliters and creating visible demonstrations of quantum mechanics operating at dimensions humans can observe directly. Quantum mechanics at human scale. These macroscopic quantum effects transform abstract theoretical concepts into tangible laboratory demonstrations that scientists can observe and measure directly. Helium-2 represents the first substance in scientific history where quantum mechanics becomes visible to human observers, bringing the bizarre rules governing atomic behavior up to scales we can see with our naked eyes. Quantum effects typically remain confined to dimensions measuring nanometers or smaller, hidden within atomic structures where individual particles follow probability distributions and wave-particle duality governs behavior. These microscopic phenomena influence chemistry, electronics, and nuclear processes, but their effects usually disappear when billions of atoms combine to form macroscopic objects that follow classical physics. Superfluid helium shatters this boundary by maintaining quantum coherence across volumes containing trillions of atoms. The concept of quantum coherence explains how helium-2 achieves its impossible properties through collective atomic behavior that eliminates individual particle identities. In ordinary liquids, each atom maintains its own quantum state, creating countless independent wave functions that interact chaotically through random thermal motions. These individual states average out to produce classical behavior when observed at human scales, masking the underlying quantum nature of atomic interactions. Helium-2 operates under fundamentally different principles, where all atoms abandon their separate quantum identities and merge into a single collective state that encompasses the entire liquid volume. This shared quantum state creates what physicists call a macroscopic wave function, a mathematical description that governs the behavior of every atom within the superfluid simultaneously. Wave functions normally describe individual particles or small groups of atoms, using probability equations to predict where particles might be found at any given moment. The macroscopic wave function extends these principles to liquid volumes measuring milliliters or even liters, enabling quantum mechanical effects to influence the motion of substances visible to human observers. This collective wave function maintains coherence across distances measuring centimeters, creating quantum effects that persist far beyond the microscopic scales where they normally operate. The quantum mechanical distinction between bosons and fermions determines which particles can participate in collective quantum states like those found in superfluid helium. Bosons represent particles with integer spin values, including photons, certain atomic nuclei, and some types of atoms like helium-4. These particles follow statistical rules called Bose-Einstein statistics, which permit unlimited numbers of bosons to occupy identical quantum energy states simultaneously. This property allows bosons to condense into collective states where individual particle identities disappear completely, creating the foundation for superfluid behavior. Fermions possess half-integer spin values and include electrons, protons, neutrons, and atoms like helium-3. These particles obey Fermi-Dirac statistics and remain subject to the Pauli exclusion principle, which forbids multiple fermions from occupying identical quantum states within the same system. This restriction prevents fermions from forming the collective quantum states necessary for superfluid behavior under normal conditions, requiring special mechanisms to overcome the exclusion principle limitations. Helium-4 contains 2 protons, 2 neutrons, and 2 electrons, creating a total spin of 0 that classifies it as a boson. This classification exempts helium-4 from Pauli exclusion principle restrictions, allowing unlimited numbers of atoms to occupy the same quantum state when thermal energy becomes sufficiently low. At 2.17 Kelvin, thermal motion decreases enough that helium-4 atoms begin condensing into shared quantum states, creating the superfluid component within helium-2. The condensation process continues as temperatures drop further, increasing the superfluid fraction while decreasing the normal fluid component that retains individual atomic identities. Helium-3 presents a more complex case due to its fermion nature, containing 2 protons, 1 neutron, and 2 electrons that produce a net spin of 1/2. The Pauli exclusion principle prevents helium-3 atoms from directly forming collective quantum states, making superfluid behavior impossible at temperatures where helium-4 readily exhibits these properties. Helium-3 requires temperatures approximately 1,000 times colder than the Lambda point, reaching millikelvin ranges where entirely different quantum mechanisms enable superfluid formation. Cooper pairs provide the mechanism through which helium-3 overcomes Pauli exclusion principle restrictions to achieve superfluid behavior at extremely low temperatures. When cooled to millikelvin ranges, helium-3 atoms form bound pairs through weak attractive interactions similar to those governing superconducting electron pairs. These Cooper pairs possess integer total spin, transforming them from fermions into effective bosons that can occupy identical quantum states. The pairing process requires much lower temperatures than helium-4 condensation because the attractive forces between helium-3 atoms are extremely weak, demanding minimal thermal energy to prevent pair disruption. The formation of Cooper pairs in helium-3 superfluids parallels the electron pairing mechanisms that enable superconductivity in certain metals and alloys. Both phenomena involve fermions overcoming Pauli exclusion restrictions through pair formation, creating composite particles that behave like bosons and condense into collective quantum states. This connection between superfluidity and superconductivity suggests that understanding one phenomenon provides insights into the other, linking seemingly different areas of physics through common quantum mechanical principles. The practical implications of understanding quantum behavior at macroscopic scales extend far beyond academic curiosity, potentially revolutionizing technologies that depend on quantum effects for their operation. Quantum computers rely on maintaining quantum coherence in systems containing many particles, but decoherence effects typically destroy quantum states within microseconds at normal temperatures. Studying superfluid helium reveals how quantum coherence persists across macroscopic scales and extended time periods, providing models for developing more stable quantum computing architectures. The connection between superfluid research and superconductor development becomes particularly crucial as global helium reserves continue declining. Scientists studying superfluid quantum mechanics gain insights into Cooper pair formation, quantum coherence maintenance, and collective particle behavior that directly apply to superconductor design. These quantum mechanical principles govern both phenomena, making superfluid helium an accessible laboratory for exploring concepts that could unlock the next generation of superconducting materials. Yet, the immediate challenge facing humanity involves existing technologies that depend entirely on helium cooling systems, creating urgent pressures that
MRI
cannot
machines
wait for theoretical
and the medical
breakthroughs
crisis.
to reach practical
Medical facilities
applications.
worldwide depend on these cooling systems to maintain the superconducting magnets that generate magnetic fields measuring 1.5 to 3 Tesla, roughly 30,000 to 60,000 times stronger than Earth's magnetic field. These electromagnets require liquid helium cooling to maintain temperatures of minus 269 degrees Celsius, just 4 degrees above absolute zero. Without helium cooling, electrical resistance would cause these magnets to overheat catastrophically, generating enough heat to destroy the entire system within seconds. The superconducting wire coils lose all electrical resistance only at these extreme temperatures, allowing electrical currents to flow indefinitely without energy loss while producing the stable magnetic fields essential for high-resolution medical imaging. Hospitals worldwide face unprecedented disruptions as 2025 helium shortages force difficult decisions about MRI service availability. St. Vincent's Medical Center in Birmingham reduced MRI operating hours by 35% after helium costs tripled within 18 months. Massachusetts General Hospital postponed equipment upgrades and limited non-emergency scans to preserve helium supplies for critical diagnostics. University of California Medical Centers implemented strict rationing protocols, requiring department heads to justify each helium delivery request. These restrictions create dangerous delays for cancer patients requiring frequent imaging, cardiac patients needing immediate diagnostics, and neurological cases where early detection determines treatment success. The medical importance of MRI technology cannot be overstated, with approximately 40 million MRI scans performed annually across North America alone. European hospitals conduct an additional 35 million procedures yearly, while Asian medical centers report 28 million scans in 2024. These 103 million global MRI examinations detect brain tumors, diagnose stroke damage, identify spinal injuries, and monitor treatment responses for countless medical conditions. Each scan requires between 2,000 and 7,000 liters of liquid helium depending on magnet size and cooling system efficiency, creating enormous demand for this irreplaceable resource. MRI imaging provides diagnostic capabilities impossible through other medical technologies, revealing soft tissue details invisible to X-rays or CT scans. Physicians rely on MRI contrast to distinguish healthy brain tissue from tumor growth, identify multiple sclerosis lesions, and assess joint cartilage damage requiring surgical intervention. Cardiac MRI reveals heart muscle scarring after heart attacks, while abdominal MRI detects liver tumors and kidney abnormalities. Emergency departments depend on MRI for diagnosing stroke patients, as rapid imaging determines whether clot-busting medications can prevent permanent brain damage. Healthcare systems struggle with economic pressures as helium costs consume increasing portions of operational budgets. Grade A helium prices reached $390 per thousand cubic feet in 2024, representing a 340% increase from 2020 levels. Larger hospitals spending $250,000 annually on helium in 2020 now allocate over $850,000 for identical quantities. Rural medical centers face even greater challenges as smaller helium deliveries carry premium pricing that strains limited budgets. Insurance reimbursement rates fail to account for these dramatic cost increases, forcing hospitals to absorb losses or reduce service availability. Helium recycling technologies offer partial solutions to supply shortages, though implementation requires substantial capital investments. Modern recovery systems capture up to 90% of helium gas that would otherwise vent to atmosphere during MRI magnet quench events or routine maintenance procedures. These systems cost between $400,000 and $1.2 million depending on capacity and automation features, creating financial barriers for smaller facilities. Installation requires specialized technicians and ongoing maintenance contracts, adding operational complexity that many hospitals struggle to manage effectively. Recovery system payback periods range from 2 to 5 years based on helium consumption rates and local pricing structures. Large academic medical centers with multiple MRI units achieve fastest returns on investment, while community hospitals with single scanners face longer payback periods. Despite initial costs, leading healthcare systems report 60 to 80% reductions in helium purchases after implementing comprehensive recycling programs. These savings prove essential as helium availability continues declining while demand increases from expanding medical imaging needs. Advanced MRI designs requiring minimal helium cooling offer potential long-term solutions, though widespread adoption faces significant obstacles. Next-generation scanners utilize sealed cooling systems containing as little as 7 liters of helium, compared to 1,500 liters required by conventional units. These low helium systems cost 40 to 60% more than traditional scanners, while producing magnetic field strengths limited to 1.5 Tesla, compared to 3 Tesla capabilities of larger units. The reduced field strength compromises image resolution for certain diagnostic applications, making these systems unsuitable for neurosurgical planning or detailed cardiac imaging requirements. Replacing existing MRI infrastructure presents enormous challenges given that over 35,000 superconducting scanners operate worldwide. Each replacement involves months of planning, facility modifications, and staff retraining while interrupting patient services during installation periods. The global manufacturing capacity for low helium MRI systems cannot meet replacement demand for decades, even with aggressive production scaling. Hospitals must therefore balance immediate helium conservation needs against long-term equipment replacement strategies while maintaining diagnostic capabilities. The timeline for complete helium depletion accelerates as the United States Federal Helium Reserve approaches exhaustion by late 2025. This strategic reserve previously stabilized global markets during supply disruptions, but mandated commercial sales eliminated governmental buffer stocks that protected healthcare systems. International production struggles to compensate for declining American output, creating supply volatility that threatens medical imaging availability. Industry analysts project 15 to 20-year timeframes for complete reserve depletion at current consumption rates, making immediate conservation efforts critical for maintaining healthcare access. Understanding superfluid helium's quantum properties becomes increasingly important as scientists search for solutions to this medical crisis. The same quantum mechanical effects that create impossible behaviors in helium-2 govern the superconducting materials that make MRI magnets possible, suggesting that deeper comprehension of these phenomena might unlock revolutionary cooling technologies that could transform medical imaging entirely. Superconductors and the future of technology. Superconducting materials share fundamental quantum mechanical principles with superfluid helium, both requiring extreme cooling to achieve their extraordinary properties. These materials exhibit zero electrical resistance below critical temperatures, allowing electrical currents to flow indefinitely without energy loss or heat generation. They also demonstrate the Meissner effect, expelling magnetic fields from their interior and creating conditions where magnets levitate above superconductor surfaces without visible support. This magnetic levitation occurs because superconductors generate surface currents that create magnetic fields exactly opposing external magnetic forces, resulting in perfect magnetic repulsion that maintains stable levitation. Current superconductor applications span critical technologies that define modern civilization. Beyond MRI machines requiring helium-cooled superconducting magnets, particle accelerators like the Large Hadron Collider utilize thousands of superconducting electromagnets to guide particle beams around their circular paths. These accelerators require continuous liquid helium cooling to maintain superconducting properties in magnetic systems, generating fields exceeding 8 Tesla. Quantum computers represent emerging applications where superconducting circuits create qubits that maintain quantum coherence through Josephson junctions operating at millikelvin temperatures. The theoretical foundation connecting superconductivity to superfluid behavior emerged through groundbreaking work by John Bardeen, Leon Cooper, and John Robert Schrieffer, who developed their comprehensive theory in 1957. The Bardeen-Cooper-Schrieffer theory explains superconductivity through electron pair formation, where electrons overcome their natural electrostatic repulsion to form bound states called Cooper pairs. These pairs behave like bosons rather than individual fermions, allowing them to condense into collective quantum states similar to those observed in superfluid helium-4. The BCS theory earned its creators the 1972 Nobel Prize in Physics for providing the first microscopic explanation of superconducting phenomena. Cooper pairs represent the fundamental mechanism enabling superconducting behavior, operating through quantum mechanical principles that mirror superfluid formation. Individual electrons normally repel each other through electrostatic forces, preventing the collective behavior necessary for superconductivity. However, at extremely low temperatures in certain materials, electrons can overcome this repulsion through interactions mediated by lattice vibrations called phonons. These phonon-mediated attractions create weakly bound electron pairs that move through crystal lattices as single entities, flowing without scattering off atomic impurities or defects that would normally create electrical resistance. The superfluid nature of Cooper pair flow becomes apparent through their collective quantum behavior within superconducting materials. Like helium atoms in superfluid states, Cooper pairs abandon individual quantum identities to occupy shared quantum states extending throughout entire crystal structures. This collective coherence enables pairs to flow through materials without interacting with individual atoms or lattice defects, creating frictionless electrical transport analogous to frictionless liquid flow in superfluid helium. The mathematical descriptions governing Cooper pair superfluidity closely parallel those describing superfluid helium, revealing deep connections between these quantum many-body systems. Room temperature superconductors would trigger technological revolutions comparable to the development of semiconductor electronics or the invention of the transistor. Electrical power transmission currently loses approximately 8% of generated energy through resistance heating in copper transmission lines, representing billions of dollars in wasted electricity annually. Superconducting power cables would eliminate these losses entirely, dramatically improving power grid efficiency while reducing environmental impacts from unnecessary power generation. Urban power systems could transport electricity through compact superconducting cables requiring minimal space compared to massive copper conductor bundles currently needed for high-current applications. Transportation systems would undergo fundamental transformations through room temperature superconductor availability. Magnetic levitation trains currently operate in limited locations due to expensive cooling requirements for superconducting magnetic systems. Room temperature superconductors would enable widespread maglev transportation networks, offering unprecedented speed, efficiency, and environmental benefits compared to conventional rail or automotive systems. Electric vehicles could utilize superconducting motors and power systems, achieving perfect efficiency while eliminating battery heating issues that currently limit performance and longevity. Computing technology would experience revolutionary advances through superconducting electronics operating without energy losses or heat generation. Current microprocessors consume enormous amounts of electrical power converted primarily into waste heat, requiring sophisticated cooling systems and limiting processing speeds. Superconducting processors would eliminate these thermal constraints while enabling processing speeds limited only by fundamental physics rather than thermal management considerations. Quantum computers would benefit enormously from room temperature superconductors, eliminating expensive dilution refrigerators currently required for qubit operation while enabling quantum systems accessible to broader research communities. Studying superfluid helium provides crucial insights for achieving higher temperature superconductivity through understanding quantum collective behaviors that enable both phenomena. Researchers investigate how helium atoms overcome thermal fluctuations to maintain quantum coherence across macroscopic scales, seeking principles applicable to electron pair formation in superconducting materials. The mechanisms enabling superfluid flow at 2.17 Kelvin might reveal strategies for creating superconducting materials operating at progressively higher temperatures, potentially reaching room temperature through enhanced understanding of quantum antibody physics. Current helium shortages create urgent pressures for developing superconducting alternatives that reduce or eliminate liquid helium cooling requirements. High-temperature superconductors discovered in the 1980s operate using liquid nitrogen cooling, dramatically reducing costs and complexity compared to helium-cooled systems. However, these materials remain limited to specialized applications due to brittleness, current carrying limitations, and processing challenges. Understanding superfluid quantum mechanics might unlock pathways to superconducting materials combining room temperature operation with the robust performance characteristics needed for widespread technological adoption. The convergence of superfluid research and superconductor development represents humanity's most promising path forward as helium reserves continue declining. Scientists pursuing room temperature superconductors through superfluid insights could eliminate helium cooling requirements entirely, transforming global energy infrastructure while preserving remaining helium supplies for irreplaceable applications. These quantum mechanical investigations promise technologies that could reshape civilization through perfect electrical efficiency, magnetic levitation transportation, and accessible quantum computing systems. The bizarre properties exhibited by this impossible liquid at temperatures approaching absolute zero may ultimately prove essential for humanity's technological future. Research into these quantum mechanical phenomena continues accelerating as the practical urgency becomes undeniable. Superfluid helium represents both humanity's most perplexing scientific puzzle and our potential escape route from the looming helium crisis. This quantum liquid that climbs walls and flows without friction holds secrets that could revolutionize every aspect of modern technology. Understanding how helium atoms achieve perfect collective motion at 2.17 Kelvin might unlock room temperature superconductors that eliminate our dependence on helium cooling entirely. The same quantum principles governing superfluid behavior could transform energy transmission, medical imaging, and quantum computing beyond recognition. The strangest substance on Earth, defying gravity and thermodynamics, may ultimately prove essential for humanity's technological survival.